Morning. Yes, last classes already we discussed about these topics. It's discrete Fourier series and discrete Fourier transforms. Just to rewind this discrete Fourier series and discrete Fourier transforms. Okay, okay. Discrete Fourier series. Okay, discrete Fourier series. Here we are considering the sequence xp of n with a period of n samples, so that xp of n, as it is a periodic signal, so with a period of n samples, it can be represented as xp of n equal to xp of n plus ln, where xp of n is a periodic. Since xp of n is a periodic, it can be represented as a weighted sum of complex exponentials whose frequencies are integer multiples of fundamental frequency 2 pi by n, so that these periodic complex exponentials are of the form e power j 2 pi kn by n. This n is replaced by n plus ln. Okay, so this is the complex exponentials form. Complex exponentials form. Okay, this is the complex exponentials form. Okay, it can be represented as e power j 2 pi kn by n is equal to e power j 2 pi k into n. Instead of n, we can write n plus ln. Okay, n plus ln, right? So let it be considered as equation number 1, where l is an integer. Okay, since the discrete time Fourier transform of a sequence is periodic, when sampled, it consists of a finite number of distinct frequency components. If the number of frequency components are n, then the harmonics are given by 2 pi k by n, where k is 0 to n minus 1. Okay, so now any periodic sequence xp of n can be expressed as xp of n is equal to 1 by n into sigma k is 0 to n minus 1 xp of k into e power j 2 pi kn by n. Okay, it is in the form of complex exponentials, right? Where the small n is varying from 0 to n minus 1. Let it be considered as equation number 2. Okay, where this xp of k, where k is equal to 0 to n minus 1, these are called discrete Fourier series coefficients. These are called xp of k is nothing but discrete Fourier series coefficients. To obtain the Fourier coefficients, multiply both sides of equation 2 by e power minus j 2 pi by n into n mn, and sum the product form n equal to 0 to n minus 1. Okay, no, so multiply this with the e power minus j 2 pi by n into mn. Okay, so sigma n equal to 0 to n minus 1 xp of k into e power minus j 2 pi by n into mn is equal to sigma 1 by n into, okay, 1 by n sigma k equal to 0 to n minus 1 already is there. So sigma k n equal to 0 to n minus 1 into sigma k equal to 0 to n minus 1 xp of k into e power j 2 pi by n into k minus m into n. This is equation number 3. Here we are interchanging the summation. We are interchanging the order of summation on the right hand side of the equation number 3, so that it will become 1 by n into sigma k equal to 0 to n minus 1 into xp of k into sigma n equal to 0 to n minus 1 into e power j 2 pi by n into k minus n into n. Let it be considered as equation number 4. Using the relation sigma n equal to 0 to n minus 1 e power j 2 pi by n into k minus m into n is equal to n if k minus m is 0, k minus m 0 plus or minus m plus or minus m or plus or minus 2n, etc. And it is equal to 0 otherwise. So we obtain sigma n equal to 0 to n minus 1 xp of n into e power minus j 2 pi by n into mn is equal to xp of m, right? xp of m, let it be considered as equation number 6. So changing the index from m to k, if m is replaced by k, then it will become xp of k is equal to sigma k n equal to 0 to n minus 1 xp of n into e power minus j 2 pi kn by 2 pi kn by n. Okay, 2 pi kn by n. Why? Because this m is replaced by k. So this equation number 7 and equation number 2, these two are referred as DFS, discrete Fourier series, and inverse discrete Fourier series, respectively. IDFS, DFS and IDFS, right? So it is clear that it is clear that both sequences xp of n and capital XP of k are periodic with period n samples. So discrete Fourier series of xp of n is equal to xp of k. So this is the relation between discrete Fourier series and xp of k. Okay. So coming to the properties of the discrete Fourier series, these are common properties: linearity property, time shifting property, symmetry property, right? And periodic convolution, right? These are all the properties of DFS. And we already discussed about the this tabular form also: linearity, time shifting, frequency shifting, periodic convolution, multiplication, symmetry property, right? So these are the properties. Next, we discussed about the discrete Fourier series representation of periodic sequences. Periodic sequences. So determine. So here we have done a small problem, like determine discrete Fourier series representation for the signal x of n is equal to cos n pi by 3, and plot this way, plot the spectrum of x of n also. Okay. Okay, right. So consider x of n equal to cos n pi by 3. So cosine function, this is cosine function. It can be also written as actually general form of the cosine function is 2 pi fn, cos 2 pi fn. So given function is cos n pi by 3. Equate these two equations. So 2 pi fn is equal to n pi by 3, or f equal to 1 by 6. Okay, the frequency is the ratio of the two integers. Here the given cosine waveform is a periodic. So f equal to k by n, that is equal to 1 by 6, or n equal to capital N equal to 6. Capital N equal to 6. Okay. Capital N equal to 6, right? So it is a period. The period is a period n equal to 6. We know that cos theta equal to cos theta formula. We already know that e power j theta plus e power minus j theta by 2. Here theta value is n pi by 3. So cos n pi by 3 is e power j n pi by 3 plus e power minus j n pi by 3 by 2. Okay. So x of n equal to 1 by 20 e power j pi by 3 into n plus 1 by 20 e power minus j pi by 3 into n. That is equation number 1. Or we can write this as sigma k equal to n ck into e power j 2 pi n k by n, right? 2 pi n k by n. Right. So here sigma k equal to n indicates summation over n number of samples. Since the sequence is periodic, then sigma n equal to 0 to n minus 1 will be same as taking summation over any consecutive n number of samples. For n equal to 6 and taking summation over k equal to n equal to 6. So for suppose if we take the 6 consecutive values from minus 2 to 3, 1, 2, 3, 4, 5, 6. So n value is 6, right? So what is the formula here? X of n equals sigma k equal to minus 2 to 3 ck into e power j 2 pi n k by n. Here n value is 6, capital N value is 6. So 2 gets cancelled 6 by 3 times. So j pi kn by 3. Okay. So by substituting values of minus 2, if you substitute minus 2 value here, we will get x of minus 2 value is 0, like this. C of minus 2, C of minus 1, C of 0, C of 1, C of 2, and C of 3. These are the values. By substituting these values in this expression, we will get these values. Okay. Similarly, right side of the expression. So we'll get the plot spectrum of cos n pi by 3 like this. Okay. Next, this is about the discrete Fourier series. Next, coming to the discrete Fourier transforms. So it is used for frequency analysis of the signal. It is given as like a Fourier transform. Fourier transform. If we take the general Fourier transform, x of e power j omega, that is equal to sigma n is minus infinity to infinity, x of n into e power minus j omega n. Here omega is angular frequency and it has the continuous range of 0 to 2 pi. Okay. Like this, the discrete Fourier transform omega is represented as 2 pi by n into k, where k equal to 0 to n minus 1. So this is our discrete Fourier transform. So the difference between discrete Fourier series and Fourier transform is like this. The DFS is a Fourier series expansion, that is discrete Fourier series is Fourier series expansion of periodic discrete time signal, and Fourier transform converts periodic or non-periodic discrete time signal to frequency domain. So Fourier transform, discrete Fourier transform means it can be translated into its domain, frequency domain. Okay, whereas discrete Fourier series is in time domain. Okay, right? So a definition of DFT and IDFT, inverse discrete Fourier transform and discrete Fourier transform. So what is DFT? How it is represented? X of k is equal to sigma n equal to 0 to n minus 1. X of n and e power minus j 2 pi k n by n, where k is varying from 0 to n minus 1. K indicates the index of the frequency. Similarly, inverse discrete Fourier transform is represented as mathematically represented as x of n is equal to 1 by n into sigma k equal to 0 to n minus 1 x of k into e power j 2 pi n k by n, where n equal to 0 1 up to n minus 1, where capital N is length of the sequence x of n. Both here x of n and x of k both contains n samples. Okay, next we have done some problems based on the above formulas. Find the DFT of the sequence x of n equal to 1 1 0, here n equal to 4, and find the IDFT of y of k equal to 1 0 0 1 0 1 0, like so. First of all, we have to find out DFT and then IDFT. So what is the formula for finding DFT? X of k equal to sigma g n equal to 0 to n minus 1 x of n e power minus j 2 pi n k by n, where k is varying from 0 to n minus 1. Here n value is 4, so it is varying from 0 to 3. Okay, 0 1 to 3, right? Similarly, so we'll find out the values of x of 0, x of 1, x of 2, and x of 3, right? So this is the sequence. X of k is this one. Similarly, IDFT. So what is the formula for inverse discrete Fourier transform? So x of n or y of n equal to 1 by n into sigma k equal to 0 to n minus 1. Y of k into e power plus j 2 pi n k by n, where n is varying from 0 to n minus 1. Here the n value is 4, so it is also varying from 0 to 3. Here also we'll substitute the values of n equal to 0 to 3. We'll get y of 0, y of 1, y of 2, and y of 3 values. So finally, y of n value is 0.50, 0.50. This is the IDFT, inverse discrete Fourier transform, right? So like this, we can find out the DFT and inverse discrete Fourier transform of the given sequence, right? Like here also, x of n is given as 1 for 0 is less than or equal to n is less than or equal to, it is otherwise 0. So here 2 bits are given. Here n equal to 4, n equal to 8, plot magnitude plot and phase plot. Okay, or amplitude plot and phase plot. So L equal to 3. For n equal to 4, the periodic extension of x of n can be obtained by adding 1 0, that is n minus 1. So 4 minus 3, that is 1. So it is called zero padding, right? This is called zero padding. So how to find out DFT? So x of k equal to sigma n equal to 0 to n minus 1 x of n and e power minus j 2 pi n k by n. Here k is varying from 0 to n minus 1. Here n value is 4, that is 4 minus 1, that is 3. Okay, we'll find out 0, x of 0, x of 1, x of 2, and x of 3 values, right? So this is the sequence given. This is the periodic extension of the sequence for n equal to 4. Like that, we can find out the values. So x of 0, x of 1. So mod x of 0 is 3, and here phase angle is 0. Similarly, k, it is also k minus j, that's why it is the angle is 1 by 2. Mod x of 1, square root of j square plus j square. So 1 plus 1, like this. So this is j, square root of j square. Square root of j square is 1. And tan inverse b by a. Okay, that is tan inverse imaginary term is there. Tan inverse infinity, that is minus 5 by 2, right? Like that, we will find out the magnitude or amplitude or phase angles. Okay, right? So here it is real term is there, and imaginary term is 0. So tan inverse 0 by 1, that is tan inverse 0, that is 0, right? So it is the phase angle. Like this, we can find out the magnitude and phase angles. So for x of 0, x of 1, x of 2, and x of 3. Like this, we'll find out the magnitude and phase angles and draw the plot between amplitude versus frequency, and phase angle versus frequency, like this. Okay. for this also, for this sequence also, we can find out the this is the bit 2. So for this sequence also, we can find out the values and draw the magnitude. We can draw the amplitude and phase plots of the given sequence. That is also like this. See, I'll find out these values. Here n is given as 8, so that the k value is varying from 0 to n minus 1. 8 minus 1, that is 7. Similarly, n value is varying from 0 to n minus 1, that is 0 to 7. So like this, we can draw the. Similarly, we can draw the 8-point DFT of the sequence in the same manner. So we'll substitute the values in this expression. We'll find out the individual values x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, x of 6, and x of 7, right? And write these values in the sequence. That is this is the sequence. And in the same manner, IDFT also, we can find out the IDFT. So this is the IDFT values. So x of n, we'll find out x of n values. 1, this is the sequence. Okay, and then we'll discuss about the relationship with DFT to other transforms. So how this discrete Fourier transform is related to other transforms like jet transform, Fourier transform. Okay, right. So first of all, we take the relationship to Fourier transform x of e power j omega. Okay, is equal to sigma n equal to 0 to n minus 1 x of n e power minus j omega n, right? X of e power j omega is continuous function of omega, right? So the discrete Fourier transform of x of n is given by x of k equal to sigma n equal to 0 to n minus 1 x of n e power minus j 2 pi n k by n, where k is varying from 0 to n minus 1. So this is the discrete Fourier transform, and above one is the Fourier transform for the complex variables. Okay, so now compare these two equations. We find that DFT of x of n is a sample version of the Fourier transform of the sequence. If this omega is equal to 2 pi k by n, if this omega is replaced by 2 pi k by n, then these two are equal, where k is equal to 0 to n minus 1. So x of k is equal to x of e power j omega. These two are equal when this omega value becomes 2 pi k by n. This is the relation between discrete Fourier transform and Fourier transform. So x of k equal to x of e power j omega at omega equal to 2 pi k by n. That is the relation between discrete Fourier transform and Fourier transform. Similarly, in the same manner, we'll compare this discrete Fourier transform with the jet transform. So what is the formula for finding jet transform? X of z equal to sigma n equal to 0 to n minus 1. X of n into z power minus n. What is x of n here? So 1 by n into sigma k equal to 0 to n minus 1 x of k into e power j 2 pi n k by n. So substitute this value in the place of x of n, so that it will become sigma n equal to 0 to n minus 1 x of z equal to 1 by n into x of n is replaced by 1 by n into sigma k equal to 0 to n minus 1 x of k into e power j 2 pi n k by n into z power minus n, right? So here extract this 1 by n outside and changing the order of the summation terms, so that it will become sigma k equal to 0 to n minus 1 x of k into sigma n equal to 0 to n minus 1 e power j 2 pi n k by n into z power minus 1 whole power n. Okay, 2 pi k by n, this is minus and the z power minus 1 whole power n. Okay, it is in the form of alpha power n. Sigma n equal to 0 to n minus 1 alpha power n is equal to 1 by 1 minus alpha, or j power n, it is 1 by 1 minus e, right? So this is 1 by 1 minus e power j 2 pi k by n into z power minus 1, right? So it will become 1 by n into z power minus n into sigma k equal to 0 to n minus 1 x of k by 1 minus e power j 2 pi k n k by n into z power minus 1. So this is the relation between z transform and discrete Fourier transform. Then we discussed about the properties of DFT. Already we discussed. Then these are the proofs. We proved these properties: linearity property, periodicity property. Okay. Next, circular time shift, and these are the properties. Circular time shift property. Remaining properties are also there. Convolution property. We'll discuss in the next class. these properties. We'll prove these properties in the remaining properties in the next class. Okay, these are properties, three properties proved here. Okay, linearity property, weighted sum at the left hand side is equal to is added with the weighted sum. Okay, so here that is a1 into x1 of n plus a2 into x2 of 1. Discrete Fourier transform of this entire thing is equal to sigma n equal to 0 to n minus 1 a1 into x1 of n plus a2 into x2 of n e power minus j 2 pi k n by n. So multiply this term with this first term and second term so that it will become sigma n equal to 0 to n minus 1 a1 into x1 of n into e power minus j 2 pi k n by n plus a2 into x2 of n into e power minus j 2 pi k n by n. Right? So that it will become a1 into sigma n equal to 0 to n minus 1 x1 of n into e power minus j 2 pi n k by n plus a2 into sigma n equal to 0 to n minus 1 x2 of n into e power minus j 2 pi n k by n. Right? So this will become x1 of k and this will become x2 of k, so that it will become, finally it will become a1 into x1 of k plus a2 into x2 of k. Right? And in the same manner, periodic property is also proved. Okay, x of n minus n plus n is equal to x of n for all n. Similarly, x of k plus n equal to x of k plus for all k. Right? So x of k plus n equal to sigma n equal to 0 to n minus 1 x of n is equal to minus j 2 by n. This k is replaced by k plus n by n. So we'll write these two terms like this: e power minus j 2 by n k by n into e power minus j 2 by n n by n. Right? Okay, so this is e power j 2 by n n by n is nothing but e power minus j 2 pi by n 2 pi n 2 pi n. This e power minus j 2 pi n value is will become 1, so that it will become sigma n equal to 0 to n minus 1 x of n e power minus j 2 pi n k by n. For integers, for integer n, e power minus j 2 pi n equal to 1. The same manner, circular time shift. Okay, circular time shift. So if this DFT of x of n is x of k, then DFT of x of n minus k, n minus n is x of k into e power minus j 2 pi k n by n. Okay, so this was also proved. Right? Now it was proved. So DFT of x of n minus n is equal to sigma k equal to 0 to n minus 1 x of n minus m into e power minus j 2 pi n k by n. Let p equal to n minus m. Right? And let p is n minus m. So n equal to p plus m. Right? So n is replaced by p plus m. So this is x of p. So p is varying from 0 to n minus 1 sigma x of p into e power minus j 2 pi k into this n is replaced by p plus m by n. Right? So it can be written as e power minus j 2 pi kp by n e power minus j 2 pi km by n. Right? So x of p into e power minus j into e power minus 2 pi km by n. Right? So this is nothing but x of k into e power minus j 2 pi km by n. So this is about the circular time shift. So like up to here we already discussed. For our understanding purpose, we discuss about the same things. If these things were repeated again, so in the next class we'll find out the discuss about the next remaining properties. Okay, with this I'm concluding the today's class, and in the next class we'll continue the proofs of the remaining properties. Thank you.